9.6 for the form of a conic. All right, here we go. So I think the book kind of makes a mess of this topic. It makes it really complex and difficult to understand. In order to understand the book, you need to know where the directrix is on an ellipse and where the directrix is on a hyperbola and that sort of thing. And while that's important to some people, it's not important to me right now. So I'm just going to show you what eccentricity is, and I'll show you how the basic form works, and I'll teach you how to kind of cheat your way through the problems, okay, to get the graphs. All right, so the first thing is you need to know that all ellipses have something in common, okay? So let's take a second and draw a few ellipses. So if I draw this really long and skinny ellipse, or this almost perfectly round ellipse, you'll notice something. When the object is longer and skinnier, the foci are actually further apart. Okay, I know that some of you have already realized this through your playing around with them. The foci are typically further apart when the object is more squished looking. Okay? But when the object is more round looking, it looks like the foci are closer to each other. Some of you kind of knew that already. Just from graphing various shapes, you realize, hey, whenever this thing is really, really skinny and B is really small, it seems like my foci are way out on the edges. You think it's possible for the foci to actually eventually reach the two vertices on the sides? Do you think it's possible for these 2 points to actually get out here?
Oh.
Isn't that a line?
That'd be a line.
Okay, so what happened, this is good thinking, what would happen is the ellipse would completely crush in on itself and form a line. It would degenerate into a linear conic. Okay? If you were to push these completely to the center, what do you hypothesize the shape would look like?
Circle.
Probably a circle. That's actually correct. Okay? So, but one thing is true about all ellipses is that the A value is always larger than the C value. Isn't that true? So A is always this length and C is always this length. And there's nothing you can do about it. A is always bigger than C. That's always true on any ellipse. And it's especially true on the second drawing. Look at the second drawing. A is much longer than C. Or sometimes we write A is double greater than C. You will see this symbol a lot in college. I don't know why the double greater than doesn't show itself much in high school, but it means extremely much more larger than C. Okay? Now,
Based on what scale did you know?
Usually this symbol is used in astronomical distances. So like we would say the radius of the sun is much greater than the radius of the earth. Like that kind of thing. Okay, but actually none of this is too removed from astronomy. When the earth is traveling around the sun, I think I mentioned this before, the sun is actually at one of the foci of the earth's orbit. So the earth is traveling around the sun in an elliptical fashion, not a circular fashion, and the sun is at the focus, not the center. How many of you knew that? Okay, so this brings up a question, what's actually at the center of our solar system? Or I should say the center of Earth's orbit.
Wait, is it the asteroid belt possibly towards the center?
No.
I'm not too sure what's at the center. I'm not sure it matters.
I think it's like
It's not causing the gravitational fields that keep the Earth in orbit.
Yeah.
The sun is, and that happens to be at the focus, see? So it doesn't really matter what's at the center so much to an astronomer. In fact, the center is rarely the focus of an astronomer's observations. The focus is the focus. The scientists prefer to talk about the focal point as 0, 0, as we'll see in a moment. Okay? Okay, so it turns out the Earth's orbit is almost perfectly circular. In fact, when the Earth is furthest from the sun, you might think, oh, that's why we have winter. But actually, it's not true. We have the winter because the Earth's axis is tilted. It's a different phenomenon. And the Earth's furthest distance from the sun and closest distance from the sun are almost exactly the same. We don't even experience much temperature change. You can see our orbit is probably more like this than it is like the longer looking ellipse. But one thing is for sure, A is bigger than C, and so we have defined this new thing called E. It stands for eccentricity, and it's defined as triple equals C over A. C over A is the ratio of the distance to the focus from the center divided by the ratio of the distance from the vertex to the center. And this is always less than 1 on an ellipse. Okay? So if anyone ever asks you, hey, what do these ellipses have in common? You can say one of two things. You can say A is greater than C, or you can say E is less than 1. They mean the same thing. E is less than 1 on an ellipse. Let's talk about the hyperbola. So in the hyperbola, yeah. Triple equal sign means defined as. E was defined as C over A. And it's actually not pronounced E, it's pronounced eccentricity. Not to be confused with 2.71. Okay, that's the E base on a log. So if somebody ever asks you, hey, what's an ellipse? You can say it's a conic with an eccentricity less than 1. And they're probably like, what? Like, oh, that just means the distance to the vertex is longer than the distance to the focus. Okay? But it's true for all ellipses. If this condition fails, it's no longer an ellipse. Okay? If C were ever, say, longer than A. But that's what happens on the hyperbola, isn't it? C is actually longer than A. Let's look at the pictures. So whether your ellipse is very wide looking or very, very tight looking, okay? Either way, this distance is called A, and this distance is called C, as you know. And notice that C is greater than A. Right? And the same is true in this picture. A is this distance. C is this distance. C is greater than A. So just the fact that it's a hyperbola tells us that C is greater than A. And if we define eccentricity as C over A, C is the bigger number, so it's going to be larger value over smaller value. In other words, it's going to come out to be something greater than 1 on any hyperbola. So you could say that a hyperbola is an eccentricity greater than 1 conic. Which brings us to the circle. Okay, so the circle is an interesting case, isn't it? Does a circle look more like an ellipse, or does it look more like a hyperbola? Looks a lot more like an ellipse. So the circle, all circles have the same thing in common. There are no foci. So whether the circle is large or small, there are no foci. The truth is, someone has pushed the focus points of the ellipse to the center. So they are actually, if this distance is A, the distance C is actually 0. The focal points have been crushed into the center. Okay? So now if you try to use the old rule for ellipses, A squared minus B squared equals C squared, let's see what happens. Let's see what happens here. Try it out with me, okay? We all know that A squared minus B squared equals C squared. What happens when C is 0? Go and solve it. No. Go and solve it. B is not 0. Solve. Set C equal to 0 and see what happens. Okay, let's just work it out, okay? On the paper. It's interactive learning, so everybody writes what I suggest you write. That's how you're going to learn the important details. So C is 0. Go ahead and solve for B. A squared minus B squared is 0. What does this imply? A squared is B squared. In other words, A is what? B. In other words, the ellipse is as tall as it is wide. Well, no wonder it's a circle. Right? Now let's talk about eccentricity. If E is defined as C over A and C is 0, what can we say is true about all circles? Eccentricity is 0. last case is the hardest to explain and understand, the parabola. Always had trouble explaining this one. I'll do my best. Let's talk about parabolas. Here's a parabola. Here's a parabola. By the way, the closer that a focus is to the vertex, or you could say if you bring the focus and directrix closer together, you'll see that the parabola responds by flattening itself. Okay? So I always like to think of this as like a bowling ball, right? If you drop a bowling ball into a paper bowl, it's going to smash it flat, right? So that's what's happening. When this point moves in further, it kind of flattens out the bowl. In fact, what do you suppose would happen if you press the vertex, or I should say squeeze the vertex completely together, bringing the focus and directrix together until it hit the vertex? What do you think would happen to this parabola? You'd end up flattening out the parabola completely and form a straight line. So you degenerate the conic into a line. Okay? So the closer that thing is, the closer that focal point is to the vertex, the narrower the parabola looks. Truth be told, this first drawing wasn't too good. This distance being greater makes the parabola look more arched. Okay? So eccentricity is a little hard to define on the parabola because we're supposed to find C and A. C is supposed to be the distance from the center to the focus. I guess this is like C, I guess. I don't know. There's not really a center. And then, remember, A stands for like center to vertex. There's no center. I don't know. These are the same, I guess. I don't know. There's not really a C or an A on a parabola in the same sense as there is on the central conics, the circle and the hyperbola. So basically what we end up with on this is 1, 1. And this is for all parabolas. So that was a little hard to explain. And part of the reason is the way we've defined C in this classroom. The way we defined C was the distance from the center to a focus point. And that's not how everybody defines a C. So some people define it as dealing with that directrix. And some people know where to draw the directrix on a hyperbola and an ellipse, which we never even talked about. Okay? So we'll skip that. Just know this, that if E is 1, it's actually a parabola. Okay? If E is 0, it's a circle. And if E is less than 1, it's an ellipse. If E is greater than 1, it's hyperbola. Now let's talk about why do we even need polar form. So let's go back to the astronomy example, right? If this is the Earth traveling around the Sun, and the Sun is located at a focal point, then why in the world would a scientist even care about the center? There's nothing there. There's nothing at the center producing a gravitational field for orbit. The focus is much more interesting to the scientist than the center is. Okay? Also, why in the world would a scientist ever use rectangular form? I mean, anyone who travels distances and navigates through space or navigates even on the Earth would use a polar coordinate system. You wouldn't want to use a rectangular coordinate system unless you're a taxi driver driving north, south, east, and west in a city on a grid, right? Or if you're in a room and you're building the walls and you want them straight. Okay, so for any distance traveling or distance measurements, polar form is the way to go, really. So why do we need a polar form? Convenience. Okay, now let's say that this was an ellipse centered at 0, 0. The equation would be x squared over a squared plus y squared over b squared equals 1. If you tried to change this to polar form, it would look like this. You guys have done this many times. You change x to r cosine theta, you change y to r sine theta. And if you begin to solve this for r, you get this. I'll skip the steps because it takes like 4 or 5 steps to even get here. But if you try to isolate r, you get this horrendous equation. It's so awful. I guess you could sort of try to simplify it by making sine squared into 1 minus cos squared or something. But look how awful it is. I haven't even square rooted yet, and it's already terrible. The reason this turned out so ugly is because I chose the center as my 0, 0 spot. If I had placed the sun at 0, 0, in other words, shifted the ellipse over, and drawn this picture, Earth orbiting the sun, and drawn my x and y axes like this, actually the polar form would have come out real clean. And it would have looked like one of the following. Watch. It would have been r equals a number over 1 minus a number times cosine theta. That's not ugly. Or r equals a number over 1 plus a number times theta, cos theta I mean. Or maybe these would be sine thetas. It would be one of these 4 possibilities. I put a number sign there because I don't want to spoil it. But the number in front of the trig is E, the eccentricity. The number on top is actually something else called EP. But the point is this, what I'm trying to get to you is scientists wouldn't even care about the rectangular coordinates. So you've got to wash from your mind the idea that rectangular coordinates are more important or better in some way. They're not. They're great for certain things. The best system is polar for the astronomer, but even the equations are simpler than ours. Okay? So these are great. These are much more desirable than even our equations with x and y. And they're not that complicated if you put the sun at the focal point. Or in other words, you put the focal point at the origin. If you call 0, 0 the focus, everything kind of just works itself out. All right, I'm going to summarize all 4 of these because the book likes you to memorize all 4 of these and what they mean. I say forget that. Let's just combine this all together. I'm going to call it r equals number over 1 minus or plus number trig. So trig means sine or cosine, not tangent. Okay? This is what you need to know. And you need to know that this number is E. The top number is something related to E. It's called EP, but I don't even care about that. Okay? I don't care about that. If I told you what the top was, it would be EP. And if I told you what EP was, I'd actually know what P means. If I told you what P means, I'd have to teach you how to draw directrix for an ellipse, which I'm not willing to do. So just memorize this, that all polar forms of an ellipse come out to this. And here's the cool part. This is not only true for the ellipse, but all conics come out to this. All of them. The ellipse, the parabola, the hyperbola, every one of them comes out to be that thing after simplifying. Beautiful. Don't even worry about the top. Question?
But is this assuming that the focus is on 0?
Yes.
Okay.
Yes, it is. But that makes sense to an astronomer because that's where the gravitational field is, right? Who cares about the center? There's nothing out there. Make sense? Okay, so new world, new rules, but it all boils down to this thing in purple, and you need to know the bottom number only there in front of the sine or cosine. Okay, so how would one make polar form simpler? Call the focus 0, 0. Okay? So let's pretend the focus is the origin, I guess. That was their reasoning. And you're going to see these problems are actually not very hard now. You'll see. Okay, so how do we make polar form as simple as possible? Make sure the focus is 0, 0. Okay, let's practice identifying eccentricity before we move on. Let's say you're given r equals 5 over 3 plus 2 cos theta. Am I saying that the eccentricity is 2? No, not quite. you have to make it look like this before you can identify your eccentricity. Okay? So this problem is problematic. If there's something wrong with this picture, you'll notice that I have a 3 where I should have a 1. Okay? There's supposed to be a 1 right here, and that's not what I have. But that's easy to fix. How am I going to make that a 1? Divide by 3, right? So I'm going to divide everything by 3 just to force that to look like a 1. Let's do that real quick. So I'm going to divide this by 3, divide this by 3, and divide this by 3. There, I did it. So what is E for this problem? 2/3. What does it mean? It's an ellipse. That's less than 1. Okay? Let's try another one. See if you can identify E on this problem. We're not even graphing yet. I'm just trying to help you to find E sort of buried in the equation. R equals 2 over 6 minus 7 cosine theta. Or let's make this a plus just for fun. You're not supposed to have a 6 there. You're supposed to have a 1 there, right? So that's easy to fix. Go ahead and divide. So this time we're dividing every term by what? 6. So what's my eccentricity? Yeah, 7/6 or 1.16. Repeating. Yeah, good. So eccentricity is 7/6, you see. You'll only know that when you have it as 1 plus something on the bottom or 1 minus something. So get that thing simplified. That's a hyperbola. You can tell because E is greater than 1. So this is an ellipse. This is a hyperbola. Now you're going above what I asked you to do. Okay? I just asked for the E. Okay, now let's go to the next one. How about R equals 5 over 3 plus 3 cosine theta? Or in fact, just for fun, let's change this to a sine now. It doesn't matter, okay? It just rotates 90 degrees, all that happens. But let's go ahead and identify the eccentricity. You're going to want to divide everything by what? 3. That, of course, includes the top. Ooh, so what's my eccentricity on this problem? Eccentricity is 1. Yes. Which means it's actually a what? If you look back in your notes. It's actually a parabola. I think a line has eccentricity infinity, but I'm not sure. That's a question I've never even thought about before. I'll have to look at that later.
Wouldn't it be indeterminate because there's no C or A value ever?
Yeah.
It's not going anywhere, so it's 0, 0.
It's like 0 over 0 kind of thing. I don't know what that means. Good questions. Yeah, those are fun questions. But remember, actually, even the circle would not really show up in this lesson. Let me explain why. If this number is 0, that's the case of a circle. But if that number was 0, you wouldn't even see the trig variable here. It would be gone. So we'll do that case, but I doubt you'll see it at all in the homework. Here's maybe what your equation would look like to start with. R equals, I don't know, 24 over 13 minus 0 sine theta. Then you would divide by 13. But what this means is it would have looked like this in the first place, and you would have known it was a circle from chapter 8. R equals a constant. That's just a circle wrapped around the pole. Focus at the pole. Focus is at the center of a circle. Okay, so this would just be a trivial case. It wouldn't even show up in this section. So your answers are always going to be hyperbola, parabola, or ellipse, is what I'm saying. Okay, now that we can kind of identify the E from the equation, let's go ahead now and do the real examples. So here are the examples I picked for today. R equals 3 over 2 plus 3 cosine theta. Okay? So the first thing you're going to do is try to identify what the eccentricity is by dividing everything here by what? By 2. Okay, this is going to give me, I'll just put 1.5 on top. And you have that. 1.5, let's see, 1.5, that's bigger than 1. So my eccentricity is 1.5. What kind of shape is it? Hyperbola. Now it's time to graph. Ooh, how do we do that? Well, like I told you before, the book likes to get you to graph these completely from in your head, okay? The problem is there's a lot of memorization. So here's what I'm going to suggest. Just make a small theta r table. Plug in 3 numbers, specifically these 3. If you want to add more, you can. I just use these 3. Let's plug in 0. What is 1.5 over 1 plus 1.5 cos theta, or cos 0? Well, cos 0 is 1, so it's 1.5 over 2.5, 0.6, 3/5. Okay? Let's plug in pi over 2. 1.5 over 1 plus 1.5 times cos pi over 2, that's just 0. This comes out to 1.5. Let's plug in pi. 1.5 over 1 plus 1.5 cosine pi. Cosine pi is negative 1. So it looks like this. Negative 3. Because it's 1.5 divided by negative 0.5. So it's basically 1.5 times negative half. Or divided by negative half. With 3 points, we can easily draw the picture. Okay? So here are my 3 points. I have 0.6 radius when theta is 0. These are polar points, guys. Okay, polar. We're on the 1.5 circle for the angle pi over 2. And we're on the negative 3 circle when we hit pi. Let's see if we remember our polar plotting. Hopefully you remember how to plot polar points. You're supposed to use these circles, right? Okay. So let's see here. 0.60 would be like right here. 1.5 pi over 2 would be right here. Ooh, careful here. Negative 3 pi. That means if you go over here to pi, you don't want to actually go to the 3rd circle. You want to go to the negative 3rd circle. So is my point over here? No, it's on this side, isn't it? Okay, what shape did we say this thing was? Hyperbola. And how did the scientists design it again? The focus was at the pole? Okay, then that means it should look like this. Actually, that was probably my vertex. Let me redraw. If you want more accuracy, you can get more points, right? You can plot more points. My focus is at the pole, see? So I'm trying to draw it where my focus is at the pole.
How can you get the box?
You wouldn't even worry about the box. That's all rectilinear stuff anyway. Those are horizontal and vertical measurements. Who cares? I have one mistake on here. The point negative 3 pi was actually one of the points on the hyperbola, so I need to assume that's a vertex, not a focus. The points I plotted were in red here, so they need to actually be on the branches. So that's a better graph. If you want more accuracy, you plot more points, right? So you can plot like 3 pi over 2, you know, even in betweens if you want, but I just do the quadrantal 1, 0, 90, 180, 270. Question? Yes. Okay, now the basic geometry here is that this distance is construct the whole rectangular equation if you wanted to. So, I mean, this is kind of fun, and we have a minute or two. So, like, if you had the fact that this was at 0 and the fact that this is at 0.6, this distance on a hyperbola, since this distance is a and this distance is c, this little distance right here is a minus c, and it's 0.6. So you could actually play around with this for a little while. Also, you know that c over a was 1.5, right? That's the eccentricity. So you could learn that c is 1.5a. Using that, you could go back, plug it in here, and you could actually find a and b and c and the full rectangular equation. You could do it. You could even find the center, which scientists didn't care about. You could find the other vertex, but something that's on an orbit is following one branch, not two. It's going to be on one of the two branches, it can't be on both. So probably not even interested in the other branch. You can find the focus, but it would take a while. You'd have to really play around with it. And it's not in our lesson. It's, can you sketch the picture roughly? Let's try another one. B, how about this one? R equals 2 over 3 plus 3 sine. Okay, so you divide everything by 3, just so you could see the eccentricity. And you can see there's a 1 there that nobody would ever write, but it's there. So my eccentricity is 1. What kind of conic is that? That's a parabola, right. Okay, this means that it's one of the following 4 pictures, guys. We know that it's a focus at the pole. So it's one of these parabolas. 1, 2, 3, or 4. Is it this one? See? Or is it this one? It's just got to be one of these 4 pictures, see? Is it this one? There's only one other possibility. Is it this one? That's why we use the table. Okay? So let's just make a quick table. We'll be able to nail that down real quick. We kind of made it multiple choice here, didn't we? If you plug in 0, you're going to get 2/3. If you plug in pi over 2, you're going to get 2/4. I'm sorry, 2/6. If you plug in pi, you're going to get 2/3. If you plug in 3 pi over 2, you're going to get undefined. Because this is going to be 1 minus 1 on the bottom. So what this means is, when you get down to the bottom, there is no point. So which of these 4 pictures, when you're down at 3 pi over 2, has no point on the axis? See, that one. See, 3 pi over 2, there's no point there on the line. So it would be this one by default. And notice, it contains the points, second ring, I'm sorry, a 2/3 ring, 0, and 2/3 ring pi. So these 2 points are symmetric over the pi equals pi over 2 line. That's these 2 points. And this is the point 0, 1/3 right here. So you can plot the table, or you can kind of turn it into a multiple choice and eliminate the bad possibilities.
If you plot the table, you get one undefined for do those 4 choices, right?
Uh-huh. So if you want to add more detail to this, this is the point 1/3 comma pi over 2. This is the point 2/3 0 radians. This is 2/3 pi radians. Notice the focus is at the pole. That was all very intentional on the scientist's part. Okay? Polar form of a conic. And then one last little disclaimer. When you hit the homework assignment, you'll see some weird ones. They don't even look like the right kinds of problems. But it's because they're trying to fool you. So let me just show you that real quick. Suppose they give you an equation like this. R equals 2 cosecant theta over cosecant theta minus 2. They're trying to mess with you. I told you that this was supposed to be a 1. How would you make it a 1? What would you multiply it by? Sine. Correct. Multiply everything by sine theta, and you're off and running. This would just become 2 over 1 minus 2 sine theta. There you go. That's better. Looks like a hyperbola with e equals 2. Notice the sine and the cosine. That just provides a 90-degree rotation like before. So it just tells you which orientation you've got. Make the table, you won't go wrong. Keep in mind the focus point is not one of the points on the conic, but it's at the pole. Homework's on that moto, okay?